So can we start now? I think how many? 28 or 27 have joined. Araf, you're able to hear me?
Yes, sir, you're audible.
Okay. So what means? Did anybody take class this lecture on nanotechnology? Something?
No, sir.
Any lecture was there? Okay. Okay. So today's lecture will be on nanotechnology. Means how? I think you have some idea about nanotechnology, something, but a little bit more information you will get today's lecture. Okay. Let me see. Okay, then we can start now. So you are able to see the screen, no? So what you are seeing here?
The campus of IIT Roorkee, which we are not able to visit right now.
This is the aerial view. So I think you might have received some email from the DSW about coming to the campus. Not yet.
Yes, sir, we received the mail that
have
they were
sort of received an email, but the point, like for the vaccination status and all that,
Okay.
but we don't know if we are being called to Saharanpur or Roorkee.
Oh yeah, one meeting was, I think maybe Saharanpur was coming up, like all of you maybe put up there or something for some days. Maybe, I don't know. Anyway, I think after midterm only you might be coming, all of you, or what else. So this is the aerial view of our main building, the main key campus. Okay. So you might be seeing the name, my name, Professor Yadav, KL Yadav from Physics Department. That is Smart Materials Laboratory is my research lab area. Okay, research lab. And then, so what is all the first about nanotechnology that we will discuss? The why means you might have also heard this term nanotechnology and seen many ads also about nanomaterials, nano things in different day-to-day life materials. Also they say like in air conditioner, even sometime like a band-aid, then you have microwave ovens and air conditioners, many things, then clothes, then cycles also they're using it, some nanomaterials. So this, if you see, that is revolutionary technology waves. So in school also you have read that basic advancement in science and technology comes about twice a century and lead to massive wealth creation. That is, if you see, initially there was textiles revolution, then railroad, automobile, computer, and nowadays it is nanotech. So others are also present, but this nanotechnology also started around 1997. But it started earlier, but the main thing, technology development started here 1997, or we came to know about this technology when the instruments were developed. So if you see, there is an introduction of the technology, then there is a widespread adoption and then saturation. So in this case of nanotechnology also, it is shown that it may saturate after 2081 or before that also, or some new technology may come before that. So what is the common thing in between all this? They have the railroad, auto, computer, then nanotechnology, all are enabling technologies. Okay. So in this, if you see on the left hand side, these are the things in natural, like dust mite, and their sizes are given 200 micrometer and 5 mm. Fly ash sizes RBC. Then you have the DNA, RNA, which comes down to the 10 nanometer diameter, and atoms in nanometer sizes. On the right side, if you see, they are the man-made things. So pin you have already seen 1 to 2 mm. But there are some materials which are made in nanometer size. If you see this zone plate of 35 nanometers, so how they have drawn, that is different techniques are there. Then you have carbon nanotubes, and this is the coral made of structure with 14 nanometers. You have carbon nanotubes as connector here. Okay. So this photograph, can anybody recognize what is the whose photograph this is?
Sir, Richard Feynman.
Sir, Richard Feynman.
Yeah, Richard Feynman. Yeah, fine. So Feynman lectures you might have studied. So how he's connected to this? So Feynman, 1959 in Caltech. Okay, so 1959, one of the conference at Caltech, Feynman told something. There is plenty of room at the bottom, and it was invitation to enter a new field of physics. That is, plenty of room at the bottom means if you go to nanotechnology or nano size, the property changes. So he said in that conference that people tell me about the miniaturization and how far it has progressed. Today they tell me there is a device in the market by which you can write Lord's Prayer on the head of a pin. And if some people are from the Merit side, you might have seen in the market, some people give you, or some other places, but I had seen in Merit. On this rice grain, they write the name, your name, they can write out many things, can write smaller things. But that's nothing, that's the most primitive halting step in that direction. I intend to discuss it is the staggering small world that is now. So he said, why cannot we can write the entire 24 volumes of Encyclopedia Britannica on the head of the pin? Okay. So there is a plenty of room at the bottom. So you might have experienced also like pen drives if you're using, or the mobiles data day by day there, or in laptops and computer. So the storage capacity is increasing with the same size, but the capacity is increasing, or the size is also decreasing and storing capacity increasing. So this you see brief history of nanotechnology, how it started. Like 1959 and 12, Feynman gives a talk describing molecular machines. Then 74 nanotechnology term was used, an ion sputtering machine was developed. The term. Then 77 Dexler originates molecular technology concepts at MIT. Then 1981 first technical paper came. Then 82 the scanning tunneling microscope was built up, and after that a lot of things started. Okay. 85 fullerene buckyball was made. 3 electrodes, third electrode of the carbon. You know the carbon has that graphite and diamond, and then fullerene buckyballs were discovered. Is made in 1985. So it was already earlier also, but at that time machines were developed like this scanning tunneling microscopes and some other by which you can tell that those things are fullerene. Okay, new name was given. Then do you know what is buckyball? Anybody? Or fullerene? Hello?
That consists
Hello?
of 5 and 6 membered rings.
C60.
C60. C60 is what is C60?
So you mean the Buckminster fullerene structure, right? The football-like structure.
Yeah, football-like structure. So you have told correctly, football. So football, if you have seen how it is made of, how many? It has some hexagons and some pentagons. So how many hexagon pentagons are there? If anybody can tell.
So 12 hexagons and 20 hexagons and 12 pentagons.
Yeah, it's correct. So if you want to make it, you have to have 20 hexagons and 12 pentagons. Out of that, you can make it. Otherwise, with only hexagons, you may not be able to complete that spherical shape. Okay, in 1990, first nanotechnology journal came up, and these are things. Then 2007, Nobel Prize in Physics was given for the what is the GMR effect, giant magnitude resistance, and 2010 the Nobel Prize in Physics goes to the two-dimensional material graphene. Okay. That do you remember? Do you recognize? Yeah, I am one of them. Then this person. He is the Don Igler from IBM. Okay, I will tell later on what is that. So what is nano? Yeah, 1/1000th of a meter. That is 10⁻⁹ meters. That all of you know. Now is something about the development of computers, related dimensions. So abacus, you might have heard, and early days you might have used this even to nursery level. Nowadays, in some schools are abacus schools are there where they teach how to count fast and multiplication division can be done. Then around 1600, the slide rules came. So these are slide rules which can be used for calculations. I have also not seen and used it, and you might same with you also. So this was in around developed in 1600. Then 1882, Charles Babbage made the first calculator, mechanical calculator. If you see, these are like the steering wheels, just you rotate number of times for some calculations, like the old telephone, the dial type telephone, where if you want to dial something, some number, then you have to dial that thing. So same here. Then 1833, first analytical engine or general purpose computer was made by Charles Babbage. And it included 5 concepts that are crucial even today, or the same thing, are being used, like an input device and a storage facility, then a processor or the number calculator, then a control to direct the tasks to be performed, like CPU, and then output device. So these are the 5 main parts still are part of the computer. And then in 1940, that is the electronic numerical integrator and a computer was made. First electronic computer, if you see, this is the 10 feet tall, occupying a space 80 by 30 feet. The whole room, it is 80 by 30 feet where this whole computer is kept. Okay. But you can compare with today's computer. So this size, 10 feet tall, occupying a space, this much is being used, was in the beginning. Now this William Shockley, John Bardeen, Walter Bretton, how they're connected then when we are talking about nanotechnology? Any idea about these 3 persons together? If anyone of you have heard it. So their invention was the stepping stone. Yeah, what was that? Transistor. So they got the Nobel Prize in 1956 for the invention of transistor in 1947. Okay. And the transistor used in the electronic revolution and compactification of devices. So if some of you might have seen the old radios which were using valves, tubes, I think you may not be knowing about the tubes, but transistors you might have studied. But still that semiconductors is not in the CBS and ITJE paper. Okay, but some other boards they have. Or now CBSE book is also having. So this 1947 development of transistor was the stepping stone for the compactification of all the devices. So what is all the fuss about nanotechnology? Then Google, all of you use Google Baba for anything. Any given search engine will give 1.6 million hits or more than that, because nanotechnology is one of the way to become the first $1 trillion market. In other fields, also defense, also they are being used nanotechnology. Can anybody tell in defense area where this nanotechnology might be used?
Neurotransmissions.
Like in Kevlar, where
Yeah, Kevlar is there. Then transmission means every defense. If you take, they are also means suppose to some enemy plane or missile is coming, you have to get the information, take decision, and fire at that one. So all these things require very fast processing. Then these helmets, these guns, clothes have, they should be very lighter and still bulletproof. And then there are that fighter planes coated with material which should not they can not be detected by the enemy. Those type of coatings has been developed. So in every field it is coming. So what is nanotechnology? Although it is widely talked, there is little consensus about this nanotome, where it begins. And this is just a statistics part from some 100 people given like that. Technology that works with elements up to 100 nanometer size, around 45% people say. Like, so that means how do you define nanotechnology? The technology that works with elements up to 100 nanometer size, around 45. That works with elements up submicron level, 17. Then technology that operates under new law of physics, around 5 people. And technology that operates at level of atoms and molecules, 23%. And others, no responses like this. This is like just like nowadays election is going on, the exit poll. Some people say they voted for someone other like that here. So these are the 4 options were given, and this many people agreed. Okay, so why this type of difference in opinion? Because if you see, we have people working in physics, chemistry also, people are working biotechnology, people are working on nanotechnology, then chemical technology, then metallurgists also work on this, and computer science mathematicians also work. So, but if you take the example of these 3, physics, chemistry, and metallurgy, so you will see that physicists will say nanomaterials are of 100 nanometer size. But if you ask chemistry people, they will tell around less than 50 nanometers or smaller are nanotechnology. If you ask biotechnology people, they are working with cells and the RNA, DNA type of things, they will say some nanometers only is the nanotechnology. But if you ask a metallurgist, they will give up to 250 nanometer is that is nanotechnology or nanomaterial. So this is depending on the perception of the people who are working there, but generally it is taken to be up to 100 nanometer size is nanomaterials. So what is nanoscale science? This is emerging interdisciplinary science involving physics, chemistry, biology, engineering, material science, computer science. So stepping towards miniaturization, so lowering of the size. So you've seen desktop, you have seen, then you have the laptops, and then you have seen the palm tops, and then these things. Still you might get some mobile phones in all the things, or some wristwatches nowadays have many functions. Okay, you can see videos also on the watches also. So now understanding the size, so how big or small we are talking about. So if you see here, understanding the size, what do you see here? This is just you are seeing some flowers, the rose flowers and the leaves here. There is a photograph of 1 meter by 1 meter, and you see it is continuum. Okay, but if you zoom in, then you see some leaves. This is a housefly sitting on this leaf. This is for 10 centimeters. Still continuous you're seeing. So if you go still further, zooming in, you see now the granulation in the leaves, you are able to see it. You might have used our normal lenses, which are being used in the labs or at home also. So if you see your own palm, then you can see that which is we are not, the details are seen through that one here, which is not visible through our naked eye. Now, if you focus still further, 100 micrometers, this is the fly's eye. It is made of hundreds of tiny facets. These resembles the honeycomb structure here. If you are, this is the same case with all the eyes, means ours also and animals also. Now, if you go still further 10 micrometers, you see this is small lenses are there with light sensitive cells underneath. These are the sensors something. And at 1 micrometer level, in between the facets are the bristles which give a sensory inputs from the source to the eye. And if you go to the bristles, 100 nanometers, the bristles are there. Then 10 nanometers at their RNA, this is the helix RNA DNA made of. Now these are, after this photograph, it is the just simulation or made figures only. So they are at nanometer, 1 nanometer, you see the atoms are shown, atoms and molecules constituting the helix. Okay, so now if you have seen from the starting, so what you say, what is nanotechnology then? So that means if you go backward, so if you have atoms then combined to form like RNA DNA helix, then forms the bristle, then the lens, other lenses are there, then combine, this forms eye, okay, and then this everything combined forms this animal, housefly and other things. So if you are asked to define nanotechnology, then how do you say? So nanotechnology is the principle of atom manipulation, atom by atom at the molecular level. So it entails the ability to build molecular systems with atom by atom precision, yielding a variety of nanomachines. So implying tailoring of the structure of material at atomic scale. So why it is so important and so promising? Because since we are witnessing novel and exotic properties of the material through nanotechnology, it's all because of the effect of lower dimensions on the behavior of electrons or carriers. Okay. Why? Because the properties of the carriers change dramatically when present or confined in a nanomaterial. So you all of you might have visited some park. Okay. So when you go to a park or playground, there you might have observed, apart from the park, the flower plants and anything, you might have seen small children's kids, then some that is in the age group of 1 to 6, 7, 8. Then you might have seen people in the age group of 10 to 20, then 20 and 40, and 20 to 50, and then 50 and above, like, or 50, 60 and above people. These groups of people you might have seen in the playground or some park. And if you have observed, you might have observed some different activities. Can anybody tell what activities you might have different if you have observed sometime in their activity? Anybody can tell? Hello.
Sir, I did not quite get your question.
Yes.
I said you have visited some park or somewhere, okay? Some park or playground, and you see different age group, means people like kids, teenagers, then elders, and then senior citizens. So what observation you have seen among their activities? Any idea?
So the energy level maybe as much as the age is more, the energy level is less.
Yeah. Yes. Okay, you have got correctly. That is energy level. So if you see the kids, that's something else is there. I will tell you. One is the energy level. If you might have seen the kids, they are roaming, running here and there. They are touching anything. They are very inquisitive. Means want to know anything. and some age groups of 10 to 20, 30, 50, they are running, talking, all these things. And then you see the senior citizens, they are sitting at the benches, some walking slowly or sitting on the benches and discussing something day to day or politics or anything, okay, or family matters. But so this behavior is due to their age group and their energy levels, okay. So I am connecting this to the nanomaterials. So if you have bulk materials and the bulk and the nanomaterials of the same material, they behave differently. So here if you see this, why the nanomaterials of the same material, like if you take gold you have seen. Now if you make it in the nano size, it will behave differently. You will see in later slides. They have some exotic properties. Like that is the effect of lower dimensions on the behavior of the electrons. So why? Because the properties of carriers change dramatically when present or confined in a nanomaterial. So okay, so these you people are also the good example of the corona period. So you know this last 2 years almost is going to happen. People are at home taking classes online and confined, not able to move out freely and playing, not going to school. Now when you are asked to move out, go for offline, so there is a reluctance or behavior, means, and many people have been gone in depression, many things has happened, and this is due to the confinement at home. So if you see same thing with the jail, in the jail people, if you have seen, suppose in the jails, some movies you might have seen, they're in a group, but if somebody, some jail prisoners are put in a confined cell like the cellular jail. So if you observe the behavior of those people, they after, means when they are not allowed to interact with outer world or anybody there, they may be okay for 1 or 2 or 3 days or some days, but slowly they will start behaving differently and they may go mad also. Okay, so that is the behavioral change when they are cut off from the society or cut off, made to live separately. It is the same thing with our materials. So when they are made in lower dimensions, and you know the property of all the materials are depending on the electronic structure and the like charge, then the thermal behavior, optical behavior, everything is dependent on the electronic structure and their size and other things. So that is written why, because the properties of carriers change dramatically when present or confined in a nanomaterial. So quantum confined systems have different properties than the bulk material. So how did we get here? Okay. So new tools, as tools change, what we can see and do changes. Okay, like if you have a better tools, you can have like earlier these online classes were there, so were not there nowadays, but after last 2 years, everything is becoming on that. So the demand for the tablet has increased and the other facilities has also increased. Okay, so new tools has come up. And similarly with, like if you are asked to write something, a very fine line, draw a very fine line, and you are given a thick brush, so you cannot draw that one. But so if you are given a thin pencil, like ballpoint pen, which comes with a very small ball, which writes it, so you can draw that thin line. So that is, it depends the new tools, as tools change, what you can see and do changes. Okay. So this optical microscope you have seen with in the labs, microbiology lab or in physics lab also. Okay, so this can you know how it is. The light, visual light falls here on the mirror, then reflects through this one. Then now you have objective and the eyepiece through which you can give. So through this you can give up to 400 times magnified. So using light to see. So the naked eye can see about 20 microns. A human hair is about 15 to 100 micrometer thick. Okay, so you can see that one because we can see up to 20 microns. And light microscope tells us to about 1 micron. Okay, So if you want to see smaller than that one, the details of this, if you see here the blood cells, just you see some spherical shapes or in the 2 dimensions, it is just this type of structure. But if you want to go to see the details, you have to have a larger focusing things, which is not possible with this optical microscope. So there are electron microscope, this type of system. It is available at IT also, many of the research labs in different places. So here it can go up to 4,000 times. So why it is that like that? Because scanning electron microscopes, what is can see small objects as low as 10 nanometers. Okay, so what happens here? Bounces electrons off the surfaces to create images and higher resolution due to small wavelength of the electrons. Here, electrons are being used. It is said, you know, de Broglie wavelength or the dual nature of matter. You know, means if a particle is moving, there is a velocity. When a particle is moving, there is a wave associated with that. So in this scanning electron microscope, we have electrons which is accelerated at a high field, and there is a wavelength associated with that, and that is being utilized here to see the structure, diffraction or reflection from the objects. And then since the wavelength is around 10⁻⁵ times smaller than the visible light, and I think you remember the visible light's wavelength range, that is 400 to 700 nanometers. So in this SEM, it is 10⁻⁵ times smaller than that. Okay, so that's why you're able to see better resolution in this one. And then we have touching the surface STM. If you see here, this is the probe by which you can see, and this scale is given 25 nanometers. So this tip is how small it is. You can see. This is about how big atoms are compared with the tip of the microscope. So you can see that one. That is the scanning probe microscope developed in 1980s, gives us to see the at nanoscale. And we can now see really small things like atoms, and it was developed around the 1980s. So scanning probe microscopes, and there we have atomic force microscope. All these things you will study later on details when you come to third year, or some topic if you take nanotechnology. So we have atomic force microscope, we have scanning tunneling microscope, and how this is the atomic force microscope, that is touch and tell. And the scanning tunneling microscope, it scans the surface. The electrical current occurs between the tip and the surface. So if you have seen here, if your any object is there, it should be metallic, and this is brought here, and if there is a biasing current, then when it is brought very close to the object, there is a tunneling current between this, and depending on the tunneling current, you can tell thus what shape and everything is there. But with the atomic force microscope, it is just like a tip by which you can, or your finger, just like you feel with your finger and tell what is the material. It's the AFM is like that. So how to characterize nanomaterials? We have X-ray diffraction machines, then scanning electron microscopes, atomic force microscopes, transmission electron microscopes. These are the things, few basic. There are many other instruments. I'm not going into that one. So these are some basic instruments which will tell you whether the material is nanomaterial or not. So there is size dependent properties. So now that we can see what's going on, how do properties change at nanoscale? You can see, what do you see here? Anything? And what? Elephant you can see, and what else is there? And the rat.
Mouse.
Mouse.
Mouse, elephant.
Elephant and the mouse is there, okay. So size matters, I have said it. That means what elephant can do, this mouse cannot do, but what mouse can do, this elephant cannot do. So it's not just how big you are, it's what you can do with it, okay? Just like you might have read Hindi poem, the Sui and Talwar ke baare mein, okay? The pen and the which is mightier, like all these things. So nanotechnology is not a new phenomenon. So at the beginning, I told that in the year 1980, okay, 1989, people started talking about nanotechnology, or 1959, a Feynman gave that lecture. So this is not a new phenomenon. The lacquerous cup of 4th century AD. So this is a cup of 4th century AD, which is, if you see here, it is looking some green and then red color. So it looks red color when it is green reflected light and red in the transmitted light. Okay. So if you see here, when it is reflected light, it looks red, green, and then light in transmitted light, it is looks red. And this is from 4th century AD. That means this nanotechnology, what term we have given in 1989 or something, this thing was developed at the beginning itself, but these terms were developed now. And people that time may be using these things, were using, and why it is showing this thing, this type of behavior. So people have done this study, and they have found that there is this. If you see, this is a 50 nanometer scale, and this is the size of the particle. So you can around 50 nanometers. So there are silver and gold nanoparticles of these sizes in the lacquerous cup. Okay, so this shows this behavior due to the nanoparticles embedded in. And you might have seen in some old some places, like if you have gone to some very old buildings, use window pans and other things you might have seen. Those are not paintings, but the embedded nanoparticles. Okay, so limits of nanotechnology is what? This is if you say xenon atoms on nickel 1110 plane. This is the nickel plate of 110 plane on which xenon atom is placed, okay, in the form of IBM. So this was done by IBM scientist Don Igler in 1986 or 1996 something, which year is exactly, because this STM and other things were developed by that time. And it took around 22 hours for him to make this that time. And nowadays it can be done within 15 minutes. And these are the other things, limits like xenon on nickel, cesium iron, and then C60 copper made like this structure, and this carbon monoxide on platinum like human. Iron on copper, something is written, maybe Japanese or Chinese, I don't know. So how to make these nanomaterials? So there are two different approaches of nanofabrication. That is, this is the structure, that is top down. Start with a big chunk and cut away material to make what you want, or this type of Legos which you might have played, like small building blocks which you are using to make the bigger things like structure. So that is a bottom up, building what you want by assembling it from small prefabricated units such as atoms or molecules. So the nanofabrication can be top down or bottom up method. So this is just fabrication comparing means how much time it takes. So this, if you see, these are the coins, Indian coins. So if you can cut it into smaller pieces, one slice per minute, how long it take to cut a coin into 1 nanometer slice? So it will take around 31.7 years to cut it into 1 nanometer slices. Similarly, if you want to take this type of things and make a big gold particle, if you could add 1 atom per second, how long would it take to create a 13 nanometer gold colloids? So that is around this many seconds or this many days. So if you add seconds per colloid, then this much needed to make a billion colloidal nanoparticles. So this is about the how much time it takes. But in the nature, if you see, those things happens very fast. So that is a self-assembly process by which it happens. And okay, but this slide shows you, if you see the last one here, this is the some structure you are able to see of 5000 nanometers. Okay, so this type of structures how to make. So this, some of you might be knowing how rangoli is drawn or screen printing is done. That is lithographic technique. Okay, so this is a lithographic technique, nanosphere lithographic technique, and that is similar to the screen printing. So you might have seen in different your t-shirts, something is printed. You know what is how screen printing is done? Anybody can tell? Screen printing. One thing is just you write it with hand, smaller things on the t-shirt, or another is when you want to do in bulk, then some printing has to be done, and that is done by screen printing. You know? Anybody?
Sir, we can guess like on the particle we are on the material we are imposing a particular design. So at the microscopic level, it might be making that design.
You might have also done like in drawing class, just if you want to draw, suppose on the drawing paper, you want to draw the shape of your hand or fingers. Okay, you just put your hand palm on the paper, take a brush, toothbrush, and take some this watercolor and dip it and spray it. So what happens? You get a shadow of that one, of print of your hand or fingers. It is the same thing here if you see. So you take a clean substrate, then drop nanospheres there with some liquid is there. Then liquid dries up, you get this type of structure. And now from the top, you spray some materials. Then that will pass through this structure, and you get this type of. You remove these balls, you get this structure. So this you can visualize like if you have take small spherical balls and large number of spherical balls. So they will be touching with each other, but there will be some gap in between them. And that forms this type of structure. And if the balls are of nano size, you will get nano size structure. And that is the, simply you can explain like this, the nanosphere lithographic technique, how it is done. Okay. So this is the, I was talking, the balls in, these are the spaces in between them. And if you just spray something from the top, it will be settling on the bottom substrate, and that structure you get. And this is given to be 125 nanometers. Okay. And these balls are of 400 nanometer diameter. So you can try with cycle ball if you get it, or at home you can do with the mustard seeds. Okay. Just take some mustard seeds and then try with spent and see how what structure you get. This type of you will get it. Or you can do with the ping pong ball also, or the marbles, anything you can try. So properties of material. How much time? What is the time now? 4:50.
Sir, it's almost 5.
So you don't have any class after that? No, today I don't have. I will take 5-10 minutes more and then finish. Okay. So how properties of materials changes, like these things, you know, property describes how a material acts under certain conditions. So different, what you look into something like the optical properties like color transparency of the material. In electrical, you find out the conductivity, physical like the hardness, melting point, chemical properties like reactivity, reaction rates. These are the properties which are we see around us and how they change with the bulk and how in their nano size. Okay, these things: optical, electrical, physical, and chemical. like color, transparency, conductivity, hardness, melting point, reactivity, reaction rates, how it changes with the size. Reactivity, you can have seen like suppose you in a coffee tea cup or a coffee cup, you put a big crystal for making it sweet. So it takes time to it takes longer time to dissolve. But if you make the powder of that sugar cube and then put it there, it dissolves very fast. Okay. So properties are usually measured by looking at large, means 10^23 aggregates of atoms or molecules. But at nanoscale, there are smaller numbers are there and they behave differently. Like if you take optical properties of zinc oxide, so if you see this is sunscreen lotion applied here. So a few years back, you might have seen some players, cricket players using this pen on the face. So those were not to scare the batsman, but just like a sunscreen because they're playing in the day and there's UV light falling on them. So that is a UV protection. So nowadays many of our people are using, this is traditional zinc oxide sunscreen is white, okay, traditional one. So why they are being used this sunscreen lotion? They block UV light, they scatter white light, visible light, and appears white. But nowadays, when you make it with, like if you see here, this is the not visible, almost clear. So that is due to the nanometer size of the particle. Okay, so these are the nanometer zinc oxide nanoparticles. So still they block UV light and so small compared to the wavelength of visible light that they don't scatter it. So these big particles were scattering, so you are busy. It was looking white, but when they are not scattered, it looks clear. Okay. Then optical property of gold. So bulk gold appears yellow in color like this, but if you have 12 nanometer size gold clusters, they would look like a red color. Okay. Then if you see, so why nanotechnology is so cool? So if you see, this is the gold, bulk gold. Its melting point is around 1064, and the color is gold color, as we say. But when you grind it to smaller particles, like 1 nanometer, its melting point becomes 700, and the color is brown yellow. Okay, the same gold in this size. Or if you make it to 20 nanometer gold particles, the melting point is 1000 and this color is red. If you go to 100 nanometer size of these same gold particles, their melting point is still 1000, but color becomes the purple pink. So if you see here, the bulk gold is melting point is something else, 1064, color is gold, but at smaller sizes they're same material, but different size they are looking like showing this yellow, brown yellow, then red, then purple pink color, and the melting point is also changed. So this is the melting point decreases dramatically as the particle gets below 5 nanometer. If you see, this is the particle radius and this is the melting point. So at bigger size, like above 10 nanometers, is almost 1000 here degree centigrade, but slowly it decreases as the particle size decreases. Okay, this is the formula how it is changing. Forget these things. That is, it is 1 by R dependence. Okay. Okay, this is, I'll tell you. So there are nanosystems. So when the if macroscopic systems are bulk materials, okay. This carbon nanotubes is there. You might study later on. Macrosystems bulk. When it goes to microsystems, this is not 10 to the minus 6, but the elementary particles. Okay. And mesoscopic systems are 1 to 100 nanometers. And so one of the requirements for the nanosystems is that if it is few nanometers in one dimensional, then it is said to be quantum well. Okay, you might have studied in quantum physics or somewhere that is in quantum well. And if it is a few nanometers in 2 dimensionals, that is a quantum wire. Okay, and if it is few nanometers in 3 dimensions, then quantum dot. Okay, so just if you take mustard seed, is very small, but if it is in nanometer size, then we say it is a some people say 0 size, but that is not 0 size. Some nanometer is there still. So these are the terminology: 1 dimension, few nanometers in 1 dimensional quantum well, few nanometers in 2D quantum wire, then few nanometers in 3 dimensions, all 3, and it is quantum dot. And why this behavior changes at smaller scale? And there is thermal de Broglie wavelength is larger than the size of the particle, then this type of behavior is observed. Okay, the thermal de Broglie wavelength of the particle is given by this formula, and if you see here, this temperature is there. Okay, consider a case when the thermal de Broglie wavelength is larger than the size. Now the particle cannot be treated classically, purely quantum mechanical treatment becomes necessary. I think you might have known this formula, you might have got particle in a box. Have you done, anybody in the class, something? I don't think so.
Yes,
Yes,
had
sir, we
the
have done.
course of quantum
Okay,
chemistry.
Yes, we had done this in chemistry, quantum mechanics.
Yeah, chemistry. So this formula, you know, the energy eigenvalue h cross whole square by 2m pi n by L. So if you take L is the length of the quantum well, so the E2 minus E1, when the L is 1 meter, so this difference energy is 10 power 20 minus 10 power minus 20 electron volt. And if you take L equal to 1 nanometer, this comes down to 10 power minus 2. And typical semiconductors materials of 1 nanometer size have 1 electron volt. That is a band gap. Okay. So energy level separation is of the same order as in the atoms. So okay. So what? Okay, I will tell here. So if you see here, these LEDs are made like blue color, white color. Earlier LEDs you might have seen early when they were coming in the market were red color, green color. So if you see here, if you change the size, the band gap is increasing, and this colors is due to the band gap only of the materials. So earlier we had to mix 2-3 materials to get a particular band gap. You know, germanium, silicon are the semiconductors, but if and they have a band gap like 1.1 electron volt or 0.7 electron volt. But if you want to go get something else in between, so you have to make a mixture of some other two, third group, fourth group, third and fifth group elements, or third and fourth group elements. Doping has to be done to manipulate the band gap so that you can get different type of materials to be done, or diodes, transistors, depending on the band gap. But due to this nanotechnology, if you see here, only if you change the size of the same material, you get different types of band gap. So with this advantage, you can make with the same material different colors of LEDs and other devices also. Okay, I think this much only in one class. I cannot complete everything for you. See here in this slide, it is electrical properties. You have a higher electrical conductivity in ceramics and magnetic nanocomposites. Then I have higher resistivity in metals with nano size. And when you go for magnetic, the increase in magnetic coercivity down to a critical size in the nanoscale regime. Then mechanical properties, hardness increases strength of the metals, alloys, enhanced ductility, toughness, and formability of ceramic. Super strength and super plasticity, they are increased. Then optical properties, blue shift is there, optical spectra of quantum confined crystallites. Then there is better chemical properties, fundamental understanding of the heterogeneous catalytic properties are there. So these electrical, magnetic, mechanical, optical, chemical, they are enhanced in some way. Okay, that much only for you. So you can read something on nano plasticity, they are increased. Then optical properties, blue shift is there, optical spectra of quantum confined crystallites. Then there is better chemical properties, fundamental understanding of the heterogeneous catalytic properties are there.